you shouldn't really stand any closer than about 2 meters in front of the gun. So everyone behind when you're pointing the gun and shooting.
You're listening to the Cosmic Cast. Hello and welcome back to another episode of the Cosmic Cast. I hope you're all very well this week. I'm John Penny-Fisher, and I'm joined as per usual by the delectable Tom Harvey.
Hello.
And the insatiable Rick Bibber here.
Hello.
And I've got a fantastic guest for you this week, straight from ESA's Oxfordshire campus. It's Dr. Dayl Martin.
Thank you, John. Hello, everybody. It's good to be here.
Well, it's a pleasure to have you. So, of course, like a few of our previous guests, you were also an alum of Manchester.
That's right.
You did your PhD here. Where did you finish? A few years ago now, was it?
It was January last year I officially
January
finished
last
it.
year. How time flies. And so you are a lunar person.
That's right.
To say. You did a PhD with Katie Joy. So tell us a bit about your PhD.
Okay, so I studied regolith simulants, which I believe you've heard a little bit about in previous episodes as well. I also studied Apollo samples, both the petrography, so looking at the minerals and the kind of glasses and things that you find in the Apollo samples. And also the main part of my project was infrared spectroscopy. So I used mid-infrared light to look at the mineralogy, the bonds that you would find within the minerals in these different samples to show what it could tell us about the conditions at the lunar surface.
So this is really cool. So I guess it's worth pointing out to the public, I guess, that a lot of the missions that fly also make very similar measurements and similar frequencies. And so it's really cool that we can basically sort of simulate spacecraft data in the lab using bits of kit, and then we can then use to sort of test and calibrate mission data, which is quite awesome. So, because you were originally linked with a mission called Bepi-Colombo that was due to fly to Mercury, weren't you?
That's right. There was the Bepi-Colombo mission to Mercury, and also the Lunar Reconnaissance Orbiter, which is already orbiting the moon and collecting this kind of data as well, yeah.
Are you still involved with that mission?
To some extent, yes. So, for example, today I'm doing lab work here in Manchester, looking at some rocks that were created in the lab, so artificial samples that are designed to represent Mercury's chemistry, and all this is still in preparation for Bepi-Colombo.
Would you say that the near infrared is some of your favourite frequencies of light?
Well, I think it's the mid-infrared, actually.
Very good.
Some prefer the near-infrared, some prefer the mid, and I stick to the mid, admittedly.
It's always good to stick to the mid.
So just about the Mercury samples, so you said you can basically simulate them in the lab. How do we know what the actual readings for Mercury is? So
this goes back to the Messenger mission, which originally visited Mercury quite a few years ago, and I think it came out of orbit about 2 or 3 years ago now. Messenger did, and that took some basic X-ray readings and spectroscopy readings of the surface to look at the chemistry and the minerals that we would find. But it was very low resolution. So the idea of Bepi-Colombo is to take much more higher resolution data of the surface. So trying to piece together the data we would get from the lab with the data we already have and the data we're going to get is kind of to learn more about the full picture of Mercury.
What will the higher resolution tell us?
For the X-ray data that's going to collect the chemical and mineral maps, I believe it's down to about a few kilometers per pixel or something, which
so
is
really
an order of
chemical
magnitude
maps.
better. Yeah,
that's
absolutely.
really cool.
When's that due to fly?
It's already
It's
flying.
already flying.
Yeah,
Oh,
it
fantastic.
launched last year.
Right.
It's going to do a flyby of the Earth-Moon system in a few months' time. So we may even get some preliminary data of the Moon surface, which will be used to test the Bepi-Colombo instruments using the Moon.
Because the orbits to get to Mercury are crazy, aren't they? Haven't you got to do some sort of weird, spiral inwards to get to Mercury? Is that how it works?
Surprisingly, it's a lot more difficult to get to the inner solar system than the outer solar system. The astrophysical description is you've got to speed up to slow down.
Yeah,
So
I think, was it Bucks Fizz said something very similar, didn't they?
did they? Oh, I don't know.
I think they came up with it.
Right.
Yeah.
The astrophysicist stole it.
That's
dated.
Before they said
That is dated.
Buck Fizz are onto something. It is a complicated procedure to get things into the inner solar system.
Yeah, so they lose energy by flying past the planet, so that it'll do 2 or 3 flybys of Earth, Moon, and then that will slow it down enough to reach Venus, and it will do a few flybys of that to slow down, then eventually Mercury.
I mean, conceptually, it's insane, isn't it, to think about this small little box just like flying around the solar system like that. It's just, it's like quite abstract to think about sometimes.
The weirdest thing is when it gets to Mercury, it's going to split in half. Because you have the plasma centers, which need a very high orbit.
Yeah.
So that's run by JAXA, the Japanese Space Agency. And then for all of the surface composition, so the chemistry and stuff, that will go a lot closer, and that's the ESA instrument set.
So you said you're looking at simulated samples. What kind of rock type is it that you're analysing?
So mostly at the moment, I'm simulating the rocks for the Moon and Mars surfaces. So for the Moon, the highlands are your anorthosite kind of materials. So a lot of those come from Norway at the moment, but I'm also looking at a new deposit in Greenland, which is quite chemically similar to what we would find on the lunar surface. On the other hand, the dark areas, the Maria, are basalt. So a lot of the basalts on Earth are very widespread. So as specifically come from Ireland and Iceland, the Deccan Traps lavas. For Mars, it's mostly carbonate materials, so clays and limestones, that kind of thing for some areas, and also the reddish sands that you would expect to find everywhere on the surface. And the reason is a lot of the missions other than Bepi Colombo are focusing on the Moon and Mars in the near term. Bepi Colombo is because Mercury's surface is quite weird. We don't have many rock types that are similar other than the very ancient ones. So it's very difficult to simulate those with natural rock types.
I guess we should take a step back a bit and say, so you're working at the Harwell campus in Oxfordshire for the European Space Agency, and you are a curator there, aren't you?
That's right.
And so you're actually very exciting. You're just starting your own lab at the moment. Do you want to tell us a bit about your lab and what you're doing there?
Yeah, absolutely. So yeah, as John says, the Harwell campus is based in Oxfordshire in the UK. It's growing to be a science and technology innovation campus, so it's attracting a lot of small businesses especially with the space industry. But there's also some larger facilities such as the Diamond Light Source, which is a synchrotron that's used to get much more high resolution data that you can get in the lab. So it's already established as a science and technology campus. The European Space Agency building was built in 2015, so it's relatively new to the campus. And the lab is called the Sample Analog Curation Facility. And the idea behind this facility is it is a central point of contact, of storage, and of distribution of these planetary analog samples that represent the rocks and soils that you would find on different planetary bodies.
But you've been responsible for building this lab. I think this is what's really awesome, is that you... So how much input did you have in terms of the planning of like room design and what instruments go where and all that kind of stuff?
It was basically my plan from the beginning. Yeah, so I was given a certain footprint, the area of the lab. But before the lab was actually built, I designed in which order the labs would be arranged, where the instruments would go. And I prepared like a future 3-year and 6-year plan of expanding the lab over the next sort of few years.
I mean, what a cool thing to do, to build a lab like that from the ground up. That's amazing.
Yeah,
so what's
it's
been,
very
I
exciting.
mean, it's been ever so fun, like picking the various instruments and stuff.
Yeah, absolutely. Some of the instruments were already designated by the Natural History Museum. So I should say the project idea of this facility was started by the Natural History Museum a few years ago. So they procured the initial set of feedstock materials like the anorthosites and the basalts, and kind of a basic set of instruments as well. And they were moved from the museum to the Harwell campus last year when the lab was finished being built. So I'm now kind of expanding on what the museum already purchased in terms of the analog and instrument samples.
So what sort of things you do on a day-to-day basis then?
So at the moment we're in the late stages of the setup phase. So a lot of what I'm doing are the risk assessments and the fire safety.
All the fun
Yes,
stuff.
they absolutely. But equally, I'm in the process of calibrating a few instruments at the moment.
Great.
Only last week I set up an infrared spectrometer and a Raman spectrometer. Again, both of which will look at the minerals that you would find in these kind of samples. So on a day-to-day basis, I could be in the lab, working with the samples with loan requests or setting up the instruments. Equally, I work with part of some of the different mission teams within ESA. So I work with the Mars Sample Return campaign. I work with the Heracles team, the Lunar Sample Return team.
Yes, we've heard a bit from Heracles the other week by Fran McDonald. Do you want to just give us a reminder of what the Heracles concept
is? Oh, yes, of course, yeah. So Heracles is the human and robotic assisted lunar surface mission. So being able to return samples from the lunar surface, potentially using the Deep Space Gateway, this habitat that would circle the far side of the moon, and then bringing those samples back to Earth. So being part of those campaigns is a really exciting part of my position, and I think being a geologist, I can provide the properties of the surface and things that they could expect to interact with from that kind of mission design point of view.
Do you have a team of people working for you in your lab?
Not yet, so I'm working on that. So I should say we've got 3 student projects on offer at the moment. The closing date for these student projects is somewhere around the 15th or the 16th of June, the middle of June.
Pass us the link and we'll stick that in the description. So if any of our listeners are interested in applying, then...
what level is that aimed at?
It's for either late stage bachelor's or master's students.
Right, fantastic. Yeah. Right, yeah. Well,
so
see below for more
3 to 6 month positions based at the lab. There's 3 different projects on offer at the moment, and you'll be able to find those on the student internships website on the ESA website. But as John says, I'll pass the link on.
And that would be essentially for them to get some lab experience with you and help out in the lab then.
Yes, exactly. But also, hopefully, it will be a good experience for them. So if for example, the project is to design a new simulant, they'll learn a lot about the physical, the chemical properties of those samples. So in order to be able to design a new lunar simulant or a new Martian simulant.
So when you say designing a new simulant, how does that process work? Does does someone contact you and say, I need a simulant for this, can you provide me with it?
Exactly, yes. Okay. Most of the time for researchers, for example, they would contact and say, what do you have in stock? And then we may modify the design a little bit. So I may add some small percentages of other minerals just to customize what we already have. Brand new simulants tend to be from a mission perspective. Yes. So if the Mars Sample Return team say, oh, we're deciding to land in this particular area of Mars, so we need a representative sample. So I would then consult the data sets we have for the surface. Which can be images, it can be spectra, it can be X-ray data, or it can be things like rover tracks or rover data that we have. And then I look for those similar properties that we would find in Earth samples and then go and basically dig it up and bring it back to the lab and modify it as needed.
We're talking pretty big batch of simulants that you'll be making and curating then, or
does it depend on the usage, what the person needs it for, I guess, as well?
It does depend on the usage, but most batches of simulant we would produce in the tens to hundreds of kilogram range. So, for example, last month and this month are the Prospect drill tests. So
Prospect is it's a mission that's flying to the lunar potentially flying to the South Pole by ESA, isn't it? That's going to be drilling into some cold material.
That's right. It's a Roscosmos-led mission, Lunar 27.
Right.
But Prospect is a drill and mass spectrometer system to extract some of this cold, potentially icy regolith at the lunar South Pole area, and heat it up and analyze it to see what volatiles are in there, especially water. So in order to do those drill tests, they needed a suitable material in order to do that. So I supplied 100 kilograms of the anorthosite material that we have in the lab for them to freeze it and then do their drill tests. Equally, I've had requests for 0.5 gram of some samples. That's usually for things like instrument calibration that requires very small amounts of sample.
What's the strangest request you've had?
I might have to think about this for a second.
Some Jupitonian simulant, please.
I guess the strangest and probably most interesting has been someone trying to land a CubeSat on an asteroid surface.
Right.
So in order to do that, they need some kind of material that's similar density and particle shape as what you would find on an asteroid. And he was doing a drop tower experiment in Bremen. So they have a huge, a couple of 100-meter high tower that they do drop experiments, so zero gravity, but for very short periods of time. So in order to simulate the low gravity environment of an asteroid, he was trying to land the CubeSat as it was dropping through, as it was falling in the drop tower.
That is very cool.
That's
So
insane.
it was a really cool experiment, and I mean, I really hope he got some good data out of it.
Yeah, it just goes splat.
Yeah, exactly.
So you're here working on some Mercurian stuff at the moment. Is this related to your job at ESA? Was it Mercurian simulants that brought you here, or is it independent?
It is a little bit, yeah. So because Mercury's surface is a little bit weird compositionally, the only real way to simulate that is to do melt mixtures in the lab. So you'll get different rocks and minerals that add up to the chemistry that you want, melt them all together, and then freeze them, and you get a kind of representative bulk chemistry of the surface.
So correct me if I'm wrong, but am I right in thinking that people think that the Mercurian surface is very carbon rich?
That's right, yeah. They think there's a lot of graphite at the
Yeah.
surface.
Wow.
So I seem to remember reading about. We talked a little bit about the lunar magma ocean and about how plagioclase forms how plagioclase floats to form the lunar crust.
Yeah.
I think I remember reading somewhere that they think that things like graphite may have played a role and may have floated and formed sort of similar primitive crusts. I don't know if that's right or not, but
Yeah, I've no idea. If it is, I mean, I
Yeah.
don't think we see any evidence of that on the moon. But
Yeah.
there's
But I guess
certainly
just what
evidence
does
that-
geology look like with such high carbon abundances is a fascinating question.
Absolutely, and I think it affects how much oxygen that the minerals can kind of react with. So you get these weird sulfur materials instead. Sulfur substitutes for oxygen in a lot of these minerals. So you get sulfur mixes that aren't stable on Earth but are stable
Yes.
on Mercury.
Is this because the carbon is preferentially reacting with the oxygen instead?
It's very low oxygen fugacities,
Right.
basically. So yes, it just reminded me actually, because I guess the closest things that we have to Mercury are Enstatite Chondrites, I think, or people
Yes.
think that it could potentially be similar to Mercurian things. And Enstatite Chondrites are fascinating meteorites because, again, they have these really weird sulfide assemblages. And because they're so reducing and there's such a lack of oxygen, you get these really weird minerals in there. You don't get your normal sort of silicates like olivines and plagias and stuff. You do get some Enstatite, which is a type of pyroxene there, but you tend to get like magnesium sulfides and like calcium sulfides and just really bizarre. The elements that would normally go into your main rock-forming minerals go into these very odd other mineral phases.
They go into native metals as well.
and into
don't they?
native metals. Yeah, they're very, very unusual.
And on Earth, they're not stable. So you try to recreate these in the lab, and you only have maybe a day or two to analyze them with as many techniques as you can before they react away again. So producing long-term Mercury simulants is definitely challenging.
Yeah. It's not only Mercurian simulants that are quite difficult to produce. There's also a difficulty with lunar simulants in producing agglutinates.
That's right, yeah. So agglutinates are thought to be on any airless body in the solar system. So it's a problem for Mercury as well as the Moon, but mainly the Moon at the moment. Agglutinates are kind of glassy particles. They're almost constructs where a micrometeorite, so a few microns or less in size, hits the lunar surface at really high speed but low mass, and that causes a flash melting event. So a small amount of material, usually very fine particles, are melted and then stuck back together very quickly on the surface. So these agglutinates tend to be very weird shapes, quite angular or recumbent. Some are even donut shapes. And they include kind of crystal fragments and glassy areas, and recreating that impact process in the lab is extremely challenging.
Yeah. Can you not just pepper in like volcanic glass into a broken up basalt, or is it not as simple as that?
It's not as simple as that usually. This has been done for some simulants. So a classic example is JSC-1. JSC stands for Johnson Space Center 1, where it was created. And they used some volcanic glass from Arizona to represent the agglutinate materials. So although this kind of has the angular shapes and the glassy nature, it doesn't have any of those included minerals. It doesn't have any bubbles that you would find in agglutinates and things as well.
Okay. Yeah, so I was going to ask, is the chemical structure, well, not the structure as such, but the chemistry of the micrometeorite preserved once it impacts then?
It tends to mostly be a mixture of the material that's melted, actually.
Okay.
So there may be a little bit of the meteorite, but very often that just vaporizes.
Away,
and it's actually the material underneath that it hits that is melted. And so the average composition of agglutinates on the moon tend to still be either Mare or Highland in composition.
Yeah.
So you've got this lab with instruments for doing analysis on the simulant collection, presumably. What are some of the more interesting analytical techniques that you can do?
So some of them are fairly similar to what you find in a standard geology lab, such as an electron microscope, or I've already mentioned the infrared and the Raman spectrometers. We have a couple of X-ray systems. So one is an X-ray diffraction system, again quite similar to some of the ones we would find in a standard geology lab. But one is an X-ray gun, which is really cool. It's X-ray fluorescence. So X-ray fluorescence is often used to get the precise mineral chemistry or bulk sample chemistry out of geological materials. But one of the problems with the simulants is some are quite high mass, large amounts of sample. Some are individual boulders that you physically can't lift. So to get things like that into an instrument is very difficult. The great thing about the X-ray gun is that it's portable. If we wanted to, we could take it into the field. If we think we found a new material that's useful as a simulant feedstock, we can analyze it there and then and get that kind of idea already. But equally, for those large cobble and boulder size samples that we have, we can just point and click and it gives us the chemistry of that rock.
How big are we talking? How big are these things?
Some of them are a meter across,
Right.
So they're far too big to lift.
In terms of the X-ray gun, how big is the?
The
portable is
X-ray gun is about 30 to 40 centimeters.
Okay, that's incredible, isn't it?
But it weighs 3 tons.
It weighs 3 tons.
It has like a built-in screen as well, so you can see the chemistry updating real time as it does more and more seconds of scans. Yep.
Wow.
But equally, it can link up to a laptop or a computer. I have a benchtop stand for it as well, where we can analyze samples in the lab environment very safely. The thing to watch out for is that you shouldn't really stand any closer than about 2 meters in front of the gun. So everyone behind when you're pointing the gun and shooting. We're also planning to have a laser particle analyzer, which uses the diffraction of light in order to work out the size distribution of particles in a simulant. So this is especially important for lunar simulants, where the particle sizes of the Apollo samples are known quite well. So to recreate the mechanical properties of the surface, it's really important to have those particle sizes correct. And we're also going to get a nitrogen glove box soon as well. So looking at samples under a dry atmosphere, so electrostatic forces, for example, play a huge part when water is not involved in the samples. So drying the samples and putting them in a nitrogen atmosphere would really help us to understand how these things behave on, the surface of an asteroid or the moon.
That's fascinating.
Yeah, it's incredible.
So what are your long-term plans for this lab then? You mentioned you had like a 6-year plan. Is the plan to continue developing new simulants?
Absolutely, yeah. So one of the topics of conversation at the moment is a simulant development program where we create maybe 5 or 6 simulants that we know are either currently in high demand or will be over the next few years, to be stored at Harwell for easy distribution to whoever wants them in Europe and internationally as well. So talks are going on about the amounts that we would need of each simulant, the type of simulant, and how much it would cost, so that we can put together a business case for starting this production. The lab itself is funded for another year or 2. So we're waiting to hear. The next round of funding for ESA is in November this year, where it decides how much money it's going to pledge to different projects over the next 3 years. So we're waiting to hear in October, November this year how much longer the lab is going to be funded for. But we have this 6-year plan already in order to build that business case.
And it seems like quite a unique facility. Do NASA have an equivalent? I'm not sure they do.
NASA have a curation facility for meteorites, Apollo samples, and stardust and those kinds of things, but they don't really have a curation facility for simulants. So the standard architecture to date has been producing a simulant en masse, so a ton or two, maybe a few tons at a time, and then once that is produced, that's the batch. It lasts for a few years. It gets shared around a lot of different labs. It's very difficult to know how it's been used, how its properties have been changed since the original stock. So part of the curation facility is to log what simulants are used for what purposes, and to ensure that the properties are standardized across all of the samples.
I mean, all critical things for a simulant, you'd think.
Absolutely.
You were talking, I remember, at LPSC to some people that were, I guess, in the private sector that were also developing simulants. How much do you worry about competition from the private sector, and how does that impact your lab and what you do?
That's a really interesting question. So the private sector has to be, it's a business in its own right, so it has to charge for the simulant use. Because the curation facility for simulants and analogues is funded by ESA, the simulants are essentially available to loan if you would like to borrow one for a particular test or public outreach or anything like that. You can send a loan form to us, we'll assess the loan form, and then if we think it'll be fine, we will send the samples to whoever applies for it. On the other hand, with a private company, some do not measure the properties particularly well, so it's difficult to know what you're buying when you get this material from them. Others don't necessarily curate it very well, so look at how the conditions of the samples change over time and things like that. One great thing about private industries is they can provide them in much larger quantities because other private sector industries such as Boeing and Lockheed Martin and the big aerospace companies need tons of this material for their test beds to drive the rovers across and to drill into and that kind of thing. So there are pros and cons for both routes.
Do you think you'd ever take some of the privately made material and store some in small quantities so you have like a record of what the composition is and all that kind of thing if the private companies are not doing that necessarily?
Absolutely. So I already have probably 6 or 8 simulants added into the collection that have been produced around the world. And that's partly to gain an insight into their physical mineralogical properties. If they've done some of their own, we can compare them to make sure that the properties of the simulants are consistent between different batches. Equally, if they don't have any data, the data that we produce is available for anyone to look at. So one thing we can do is send that data back to them so that it's more helpful for them to understand the properties.
Do you do that
of
for free
materials.
then? You just say, give us your samples and we'll do some analyses for you?
It depends on the simulant and where it's come from and what its uses are. If we think it will be a useful addition to the simulant collection, then yes, definitely. If it's a kind of remake of a simulant that already exists, then it's probably not, because there are essentially higher priority simulants in the list.
I guess what you're saying though is it's not a competition.
No,
it's a collaboration.
Oh, absolutely, So that's another great thing about the lab is we have the capability for research. So one of the things I'm working with is building up collaborations with other entities on the Harwell campus itself, so local collaborations. European collaborations with different universities, different companies, these aerospace companies that need to test their rovers and things, and also internationally. I mean, I have a project with the Australian synchrotron at the moment, so these simulants really are going all around the world, and, from the collection.
No, that's absolutely amazing. Have you ever been tempted to get some of the Martian simulants, sort of spread it around a bit and pretend you're walking on Mars?
It's funny you should say that. We're tempted to do things like tables or other kind of items of furniture that incorporate the simulants as part of the design. It's a table that has, say, the lunar footprints
that's
in
awesome.
the materials and things like that. So
that's a nice little side business, isn't it?
Absolutely.
I've got quite a specific question for you. So the listeners already know that I study river valley networks on Mars. And one of the difficulties in trying to gauge how much water was on Mars flowing down these rivers is the calculations often require you to know what the sediment size is and the distribution of the sediment size as well. How do you do that for your Martian simulants?
That's a very good question. So most of the data either comes from the rover measurements, the photographs of the surface, but as you well know, the surface is quite varied. So just because a rover has collected some data from one place, it doesn't mean it's applicable to all of the different river systems. So what we can do is look at the thermal inertia of the surface. So how quickly it warms up in the morning and cools down in the evening. And that can relate to particle size distribution. So we can say, if it has a high thermal inertia, I can't remember which way around it is, but that would ideally link to a either very small grain size or a very coarse grain size.
I guess all these simulants ultimately have like an error associated with them, I guess. And I suppose some of the Martian ones probably have quite a high error at the moment, I guess.
Yeah.
Absolutely. I mean, a lot of the Martian simulants have a better spectroscopic profile because we have a lot of remote sensing data associated with Mars. What we don't have are the actual samples. So things like the physical behavior of the surface is not particularly easy to represent.
This is not a particularly interesting question, but do you also do Western simulants as well, out of interest?
At the moment, no, we don't. There is an organisation over in the US who are looking at asteroid simulants with Vesta in mind. But because there aren't many upcoming missions, near-term missions to Vesta, it's not a high priority on the list at the moment.
It's easy to forget that we have a lot of meteorite samples from Vesta. These are called the so-called Howardites. Supposedly, it's not been proven, but it's an interesting collection of rocks that often get shadowed, I guess, by the more sort of sexy lunar and Martian meteorites, I suppose, but it's still a very interesting class of meteorites in their own right.
Absolutely. I mean, one way of generating a simulant that has been proposed is to get some of these meteorites, whether they be from Vesta or even lunar meteorites, and crush them to achieve the particle size distribution.
Well, I mean, there's some quite large Vestan, or Howardites, I should say, rather, meteorites out there, and they're definitely less expensive than some of the lunar stuff. So if you had enough money,
Absolutely.
Do visit my eBay channel.
But essentially, what you do, Dayl, is such an important job in terms of
it sounds like you're integrating a massive range of different topics kind of together in order to... I mean, if you're doing particle size analyses and also chemical analysis and stuff, it's really cool that you're able to work in such a wide kind of scientific framework.
Thank you.
It's a very unique lab.
Steadily becoming a jack of all trades, because to understand the mineral properties, the chemistry, the mineralogy, but also the physical properties of all of these different planetary bodies it's a challenging amount of data to kind of integrate.
Well, I guess what we would say is that you may well be a jack of all trades, but it's fair to say that you are master of all.
Well, thank you very much.
Not a master of none. That's the rest of the saying.
Thank you for explaining that, because I was concerned that I might not understand it.
And if you ever want to take John's position on the podcast, feel free.
If you want to be master of that trade as well, then...
That was a very fascinating conversation into the weird and wonderful world of simulants.
Incredible.
So, Dayl, thank you very much.
No problem.
And
it's great to be back.
there are a lot of questions we didn't even get to cover. So, if you're in the Manchester area again, we definitely want to get you back on at some point.
Yeah. Sounds good. I'll definitely sign up.
Yeah.
So, if you weren't doing this, what else would you be doing? What else do you find fascinating outside of your field?
Well, in the area of science as well, I mean, I find ore mineralogy quite interesting. I mean, I originally started a geology course in order to go into the mining industry. So I could always venture going back. I mean, I visited Australia a couple of years ago, and Perth is heavily dominated by the mining industry, and I would absolutely love to work there. So that's one option. Okay. Equally, on a side note, I quite like things like metal forging and things like that.
You do that as a hobby. I'd forgotten about that.
So if I could, I mean, maybe open my own forge or something would be really cool.
Very cool. What sort of things have you learnt to make?
Well, at the moment, I'm making a chainmail shirt.
Wow. Let me just drop that. That's very cool.
I'm going like high nerd level here in the sense I'm making a book replica of the mithril shirt that Frodo wears in Lord of the Rings. So
Amazing.
It's slightly different to the movie version, so it won't be an exact prop of the movie. But
where do you do that?
I do that usually at home in front of my TV. It's almost like knitting, just with metal rings.
But what? How? What? Presumably you need to melt the metal to make the chain links and...
No, I have the rings already.
Right. And did you make those rings, or are they pre-made?
The wire is pre-made, so I would wrap the wire around a mandrel,
right.
And then I would cut along that spring. Essentially, you make a spring, and then you cut along that spring, and you get a lot of individual rings, and then you weave the rings together into the pattern that you need. So it's almost knitting with metal.
Amazing,
wow.
Absolutely amazing.
So I can do that in front of the TV at night. Is amazing.
Why did we even bother talking about all that simulant stuff? Well. Just to say thank you very much, Dayl, for coming on again.
Well, thank you for inviting me. It's great to be back in Manchester.
It's great to have you here. And as we said, we'd hope to have you on again.
Yeah, and we can talk more about your forging, actually.
Yeah. Well, absolutely.
So thank you very much.
Okay, thanks guys.